Hello, welcome everyone, and today's lecture will be on combined loading of beams with circular cross-section, and specifically we will look at a beam that has an L shape. So these kinds of beams are actually quite common in many engineering structures, and it's actually a fairly simple problem to start learning about combined loading. Okay, so what are the objectives of this lecture? So by the end of the lecture, you will be prepared to do one thing, which is essentially determine the normal and shear stress at specific locations in a cross-section, okay, for a beam that is subjected to combined loading. So what I mean by combined loading is that you have potentially bending, you have torsion, and you have axial loading. So these are the three loadings that you learned in your solid mechanics class, but you would have analyzed them separately. So essentially you would have looked at problems where there's only torsion, where there's only bending, or where there's only axial loading. Okay, so here we are going to look at a case where all three loadings are acting on a structure simultaneously. Okay, so let's look at the problem. So here, in this case, we have an L-shaped beam, okay, which is fixed at one end. And at the tip of this beam, you essentially have three forces acting in the X, Y, and Z directions. Okay, I want you to pay attention to a couple of things here. The first thing is the coordinate system. So X is going that way, Y is going along the axis of the beam, and Z is the vertical axis. Okay, and in this particular problem, we are asked to find out the stresses at two specific locations, point A here and point B here, at a specific cross-section in this particular beam. So this particular cross-section is 8 inches in this direction, and the arm here is 12 inches. So essentially, we are not trying to find out the maximum stress or the maximum bending stress or the maximum torsional stress in the entire beam. Rather, we are trying to find out the stresses, the normal stress and the shear stress at specific locations at a particular cross-section. Okay? So whenever you have a problem like this, the first thing that you have to do is find out the internal reactions at the cross-section where these points are located. So if you look at this point A and B here, we essentially have to find out the internal reactions, the internal forces and the internal moments that act at that particular cross-section. Okay. Once we know that, then we can relate those internal reactions to the stresses. Okay, and that is essentially what you're going to do. And again, when you want to find out the internal moments and the internal forces, you always have two options. One is that you can actually take a section there and then look at the right segment here from this point on to this point, or you can look at the left segment. Okay, you can always find the internal reactions by looking at the free body of either the left segment or the right segment. In cases where you have a fixed end, it is always a little bit simpler to look at the right segment here because you don't have to find the reactions at the support here. Okay, if you want to make a section here and then consider the left segment, then first you have to find the reactions at the support and then you have to analyze the problem. But on the other hand, if you just analyze this part here after you take the section, then you don't have to find out what the reactions at the support are. You don't have to do that. Okay, so that's why you are going to look at the right segment here. Okay. Now, when you want to find out the reactions at a particular cross-section, there are again multiple ways of doing so. One is that you can essentially find out the moments and the forces directly. So for example, if you want to find out the moment at this particular section here, then all you have to do is essentially take the formula for moment, which is R cross F. So essentially you have a force that is combined of three particular forces here, Fx, Fy, and Fz. Right? You can essentially find out what the F vector is. Then you can find out what is the R vector from that particular point or the middle of that cross section. Then you can do an R cross F and find out what the moments are. Okay, that is one way of doing it. Okay, it is good to do that, but usually it becomes more complicated when you have stresses or forces acting at multiple points. Then you have to do an R cross F for every set of forces. Okay. So what we'll do in this class, or what we'll do in this particular problem, is actually try to figure out what types of forces and moments each one of these forces are going to do or cause separately. okay, and then analyze it. Okay, it is a little bit more, I would say, it takes a few more calculations, but the reason that we're doing is this because you get a good intuition of what kind of forces and moments a particular kind of force provides, and what kind of stresses will actually come out of those moments and forces. Okay, so essentially what we're going to do is we're going to look at the effect of each one of these forces separately and figure out what kind of stresses they will cause. Okay, again, this is a little bit longer, but it helps you provide or gain intuition on how to solve this problem. Okay, so let's go ahead and do that. Okay. So what I'm going to do is first we are going to look at what kind of forces and moments will be caused by each one of these forces. Okay, so first let's look at the 600-pound force here. Okay, and what we have done here is that we have essentially made a cut here at this point. Okay, and we essentially isolated this body here, which is essentially what is shown here. Okay, so now if you look at this free body, it is very easy to find out what the internal forces are going to be. Whatever the direction of the applied force here, the force there has to be in the opposite direction because it has to be in equilibrium. So if you have a 600-pound force acting upwards here, there has to be a 600-pound force acting downwards there. Okay, just to satisfy force equilibrium. Okay, but if you want to look at the moment equilibrium, then we have to think about what kinds of moments each one of these forces here are going to cause at that particular location. Okay, now what I have done is that I have assumed specific directions for the internal moments here. So I am assuming that the mz at this point is going to be pointing up. The my at this particular cross section is going to be pointing to the left. And the mx at this point is going to be pointing in this direction. Okay, so I'm assuming those. If my assumptions are correct, then I'll get a positive value. If the assumptions are wrong, then I'll get a negative value for that. Okay, so then you can always change it. Okay, now let's look at each one of these forces separately. Okay. So if you look at the 600-pound force here, what kinds of moments will it cause? Okay, so the first thing we have to notice is that if the force is along the z direction, it cannot cause a moment in the z direction. Okay, so the 600-pound force here will not cause an mz. Okay, it can cause only an mx and an my. Okay, and in this case, it will actually cause both because there is, if you want to think about the moment about the x-axis, there is an arm here, so of 8 inches. So that force will cause an mx. And similarly, it will also cause a moment about the y-axis because it also has an arm of 12 inches there. So this 600-pound force will cause both an my and an mx. Okay. On the other hand, this 800-pound force here will only cause an mz. The reason is that, of course, it is parallel to the y direction, so it cannot cause any moment along the y direction. But it also doesn't cause a moment along the x direction because this 800-pound force would actually intersect the x-axis. Okay, so essentially the arm is 0. So essentially it will cause only one particular moment, which is going to be mz. By the same argument, this 500-pound force here is only going to cause a moment about the z-axis because it is parallel to the x-axis here, so it can't cause a moment, and it will intersect the y-axis. Okay, so it can't cause a moment about the y-axis either. So it's going to be causing only an mz. Okay, so the reason that we are doing this separately is because now you get an intuition or a clear idea of what kind of forces will cause what kinds of moments. Okay, then the question is what kinds of stresses will each of these moments actually produce. Okay, that is kind of the second part of the problem. Okay, so now once we know which particular forces are going to cause which kind of moments, then essentially we can use moment equilibrium. So first I'm going to look at the sum of moments along the z direction at the cross section about the point AB or the cross section AB. Okay, so if you do that, you have the assumed moment, which is mzAB at the cross section. Okay, and we know that both the 800-pound force and the 500-pound force are going to cause a moment about the z-axis. The moment that is caused by the 800-pound force will be 800 times, that is 800 times this length, 12. So that is here. And for the 500-pound, it's 500 times 8, which is the length here. And the sum of all those moments should be equal to 0. Okay, which means that your MZAB is going to be minus 13,600 pound inches. Okay, all that it means is that this moment is actually not going to be pointing up, it's actually going to be pointing down. Okay, the magnitude of the moment is going to be 13,600 pound inches. Okay, this is essentially just moment equilibrium. Okay, so we can do the same thing for the moment about the y-axis. Okay, and if you do that, then essentially you again go through which particular forces are going to actually cause an my, and then you use that equation and you find that my is going to be minus 7,200 pound inches. Again, what it essentially means is that the moment is not going to be in this particular direction, but actually in that particular direction. Okay, and you do the same thing for the moment about the x-axis, and you find that mx also turns out to be negative, which means that the moment is going to be pointing that direction. Okay, so let me just put it out there. It is going to be pointing in that direction. That is going to be the direction of mx, and the value of that moment is going to be 4,800 pound inches. Okay, so here there's something that is very important that I want to emphasize. Okay, so when we did this problem, okay, and then we looked at the right segment here, what I'm essentially looking at is we made a cross section, and then we are looking at this cross section. Okay, at this cross section here. Okay, and that particular cross section, you basically have these values. But when you take a section, you actually create two surfaces, right? And this is the surface that is actually still, this is a surface that is still attached to the base of the base of the L-shaped beam. Okay, now all our analysis has been done on this particular section. Okay, and the normal to that particular section is actually the minus y direction. Okay, not the positive y direction. So essentially we are looking at this section here, and the normal to that is the minus y direction, as this is the positive y direction. Okay, now what we want to do is that if you look at the opposite section here, okay, then the moments that you calculated are exactly going to be in the opposite direction. Okay, so if you take, this is something that you should have learned in your statics and definitely in your solid mechanics. So essentially, if you take a free body and then you take a section and then you look at these two segments separately, the direction of the internal forces in these particular two segments are going to be exactly in the opposite direction. So if there is a my like that here, then there has to be a my like that there. Okay, only then the equilibrium will be preserved. Okay, so that is something that I want you to keep in mind. So if you take the section whose normal is the positive y-axis, not the negative y-axis, then all these values that we got here, okay, will be reversed. Okay, that is something that you must keep in mind. Okay, so now what I have done here is essentially I have drawn the section whose normal is the positive y-axis. Okay, and in those cases, all these signs will change. So here we have minus 4,800 for the x. That becomes positive 4,800 here. Okay, so mz was minus 13,600. Now it is plus 13,600. Okay, and my, which was actually like which was minus 7,200. Okay, which is going in that direction. Now it actually becomes an my that goes in that direction. It's the opposite direction. Okay, so this, whatever I have drawn here, is basically the cross section to the left, and I have drawn each one of these moments with the right sign or the right direction and the right magnitude. Okay, so essentially you can think of that this is the cross section that you're analyzing now, and these moments my, mz, and mx are with the right magnitude in the right direction. Okay, now we can find out what kind of stresses they are going to cause. Okay, now if you think about the point number A, okay, point A, right? There is going to be a force, okay, which is 800 pounds here, that comes directly from the force equilibrium, okay? That is going to cause a uniform axial stress across the entire cross section. So whether it is point A or point B or any other point in the cross section, there is going to be an axial stress just because of that axial load. Apart from that, you are going to have stresses due to the moments. Okay. One thing that I want to notice, I want to emphasize is that there are also two more forces, which is this 500-pound force here and the 600-pound force here. Okay. Those forces are shear forces. Okay. And in this particular class, we neglect the effect of direct shear forces. Okay. We only take into account the effect of the axial forces and the bending moments and the torsional moments. We don't take into account the effect of the direct shear forces. So this 500-pound force and 600-pound force we are going to ignore. Okay? But we are still going to consider the normal force, which is this Ny. Okay? So what is the stress that is going to be caused by this normal force? It's going to be a normal stress, and it's fairly simple. It is going to be just the force divided by the area. That is going to be the stress in the y direction. Okay? Now, if you look at the moments mx and mz, both can potentially cause a stress in the x direction, a normal stress in the x direction, because they are both bending moments. But for the case of point A, it is actually lying on the x-axis, okay? Which means that the bending stress due to mx will be 0, because the perpendicular distance of A from mx is going to be 0. Okay? So the only stress that is actually going to occur due to the only normal stress that occurs at point A is going to be due to mz. Okay? And how do you find out what is the direction of the stress and what is the magnitude? It's fairly simple. You have mz, then you use your right hand rule, put your thumb along the mz direction, and you see that it is curling in. So this point here is going to be under compression, okay? Because that is where your fingers will push into. A is the diametrically opposite point, which means that it is going to be under tension, okay? So the point A is going to have a sigma y, because again, remember, the y-axis is along the axis of the beam. So the bending stresses will always be having the same subscript as the axis. So it's sigma y, not sigma x or sigma z. It's going to be sigma y, which is going to be mz times c, which is the radius, divided by I, and that is going to be a tensile stress. Okay. So essentially, now if you look at point A, we know there is going to be a tensile stress, there's going to be an axial stress due to this Ny, okay, and there is going to be an axial stress due to the bending moment mz. Okay. Now, the moment my though, okay, that is a torsional moment, which is different, okay, and that is going to cause a shear stress or a torsional shear stress, to be more precise, okay. And again, that is actually fairly easy to evaluate. So it is going to cause a shear stress tau, and that is going to be equal to Tc over J, where T, the internal torque, is nothing but the My that you calculated. Okay. So now, if you look at the sigma y at point A, which is the normal stress, it is going to be 800 over A. Okay. This is the part here. Okay. And there is going to be this part here, which is the stress that comes from the bending moment mz. Okay, so essentially, both of them are in the same direction. Remember, the stress due to the normal force is positive, because if you look at the direction of the normal force, it is along the positive y direction. So that is positive, and the stress due to the bending moment is also positive. Okay, so you add them together. Okay, so that is why you have this positive sign here. Okay. So if you do that, of course, then you can calculate what the area is, what the moment of inertia. These are actually fairly simple, and then you come up with a value of 17.6 pounds per square inch. That is going to be a normal stress at point A. And of course, you can also calculate what tau is, and that is going to be 4.584 KSI. But one thing I want you to notice here is that there is a specific subscript for this tau, which is tau yz. Okay? So what you have seen is that if you look at this particular problem, we know that the my is pointing into the cross section here. Okay? My is pointing into the cross section. Okay? So what that means is that if you look at the torque, I put my right thumb into the cross section and the direction of torque is this way. So the torque is that way, as I have noted here. Okay? So if there is a torque that way, then the shear stress at point A is going to be in that direction. Okay? Now, once I know that, I can find out what is going to be the subscript for tau yz. The normal to that cross section is y. Okay? And the direction of this force is in the positive z direction. Okay? So that is why you have this tau yz. This one corresponds to the normal to the cross section, and this subscript corresponds to the direction of force or stress, whichever way you look at it. Okay? And that is why it is tau yz, and it's a positive value because it is pointing in the positive y direction for a cross section whose normal is in the positive, it's pointing in the positive z direction for a cross section whose normal is in the positive y direction. Okay? So that is essentially everything that we need to know about the stresses at point A. Okay? And we can repeat the same thing for the stress at point B. Okay? For this point B, again, you are going to have a contribution for the normal stress from the axial force or the axial internal force, which is nothing but 800 over A. Okay? But for point B, things are a little bit different. Okay? Point B actually lies along the z-axis. So there will be no contribution to the normal stress at point B due to mz. On the other hand, mx will contribute. Okay? Mx will contribute and form a bending stress at point A. So the mx, if you think about it, you have to think about what kind of stress it is going to cause. If you go back a little bit, we know that mx is positive. It is 4,800 pounds. So put your hand, right thumb, along the direction of mx and curl your fingers. And if you do that, you are going to be pushing into point B, which means that the bending stress at point B due to mx is going to be negative. So that's why you have this negative sign here. Okay, it's going to be minus 4,800 times c, which is 1, divided by I, which is pi over 4. And that's why the stress due to mx is going to be negative. Okay? And of course, you're going to also have a torque, which is my, and that will cause a shear stress. The torque is going to be the same across the entire cross section, and that is going to be 7,200 pounds. Okay? And if you look at the cross section here, remember the torque is in that direction. That is the direction of the torque, and this is your z direction, and that is your that is your x direction. Okay? So if you look at point B here, the force is going to be in that direction. Okay? That is the direction of the torque, so the force is going to be in that direction. So if you look at that particular case, the normal is still going to be a positive y-axis, but the direction of the force here, okay, due to this torque, is going to be in the minus x-axis, along the minus x-axis. That is why your tau yx is actually negative. Okay? Tau at this point A, tau yz was positive, whereas tau yx at point B here is negative because the direction of the force is in the minus x direction. Okay? But the value is still going to be the same. It's still going to be 4.858 for KSI, it just has a negative sign. Okay? Now, if you want to find the total normal stress at point B, you have this contribution from the axial force, and then you have this contribution from the moment, mx. Okay? And if you add them together, then you get a value of minus 5.86 KSI. Okay? So now what you see is that the stresses at point A and point B are different both in magnitude and also in terms of sign. So at point B, the stress is negative, the normal stress is negative, and it's minus 5.86 ksi, whereas the stress for our point A is positive, and it's a different value, which is 17.6 ksi. Okay. So now what we have done is we have essentially found out the normal stress and the shear stress at two different points in the cross section. Okay. And essentially you can do this for any point on this cross section, fairly straightforward manner. Okay. Now, if you want to do at an arbitrary point, okay, which is not located along either the z-axis or the y-axis, then we can always use the formula that we derived earlier for the bending stress, which is that. The only difference is that you now have to take into account the effect of the axial force. Okay, so this part is the bending stress, and this part is essentially the contribution of the axial force. Okay, so this part here we already derived. It's minus mx z over ix plus mz x over iz. Okay, this is something you know how to derive, but now you have to take into account the fact that there's also an axial stress from the internal axial force. Okay, and once you do that, you can essentially substitute the locations of any point here, which is going to be x comma z. Okay, you put that into this formula, you put the z coordinate, you put the x coordinate, and then that essentially gives you the sigma y, because this ny over a is constant for the entire surface. Okay, so this is something that you must keep in mind. So when you have an axial force, it is going to cause an axial stress, uniform axial stress across the entire cross section, whereas the bending stress is going to vary across the cross section. It depends on the specific location you are in that particular cross section. But once you know the formula for the bending stress here, then you can essentially just substitute that particular coordinate into that equation and you can get the value. Okay, so I would really encourage you to actually use this expression here, okay, and then put the coordinates of A and B into that particular formula and see whether you're actually getting the same values that we got for the normal stress from the previous approach. Okay, and you can also try finding out mx and mz at the cross section directly using r cross f. Okay, and then put that value into this particular expression and see whether you get the same values that you got. Okay, so we have taken a somewhat longer approach here, but this is an approach that actually gives you a better feel of what kind of forces causes what kinds of reactions and what kind of reactions cause what kind of stresses. Okay, but if you want to do it faster, okay, then for some of these problems like this, it might be easier to calculate the internal reaction, especially the internal moments at the cross section, directly using R cross F, and then use a formula like this to find out what the normal stress is. Okay, I hope that is quite clear, and I would really encourage you to kind of redo this problem and then try to find stresses at different points and see whether it actually makes sense, whether it makes sense intuitively, whether it makes sense mathematically, and so on. Okay, hope it was a good a long problem, but hopefully you got something out of it, and I'll see you in the next class.